Have you ever wondered how 3D graphics engines render those massive, immersive virtual worlds? Or how machine learning algorithms manage to process millions of data points in just a fraction of a second? Well, the answer is actually matrices. They are essentially the invisible mathematical engines powering our entire modern digital landscape. Welcome to The Explainer. Today we're diving into a scaffolded, step-by-step masterclass to completely conquer Unit 3 of discrete structures. We're going to build your understanding of matrices right from the ground up.
All right, here's our roadmap for today. We're dividing our journey into 6 parts, starting with the absolute basics and types, moving through operations, determinants, inverses, solving linear systems, and then wrapping up with eigenvalues, eigenvectors, and some crucial exam tips. This maps directly to what we need to cover for the core syllabus. We're moving sequentially, straight from the absolute basics all the way up through Cramer's rule and eigenvectors. Because in linear algebra, every single new tool leans right on the last one you learned. So, let's jump right into Part 1, Basics and Types. This is where we lay down our foundational building blocks. At its core, a matrix is really just a rectangular grid of numbers. But here's the golden rule, and you've got to remember this. Its order is always rows by columns. Always. So, if you have a grid with 2 horizontal rows and 3 vertical columns, that's a 2 by 3 matrix. Honestly, getting this backwards is where most exam mistakes begin, so let's lock that rows by columns rule in right now. Now, we can cleanly classify these grids into different types. For instance, a square matrix has an equal number of rows and columns, while a zero matrix is, well, exactly what it sounds like, all zeros. But I want you to keep a very close eye on the diagonal and identity matrices. A diagonal matrix only has non-zero numbers cascading down that main diagonal, from top left to bottom right. And the identity matrix, that's a special diagonal matrix where all those numbers are simply ones. Keep the identity matrix in the back of your mind. It acts just like the number 1 in regular algebra, and it's going to be a massive time saver for us later. Another fundamental concept is the transpose. When we transpose a matrix, we simply swap the rows and columns. Visually, think of a flat 2 by 3 grid standing up to become a taller 3 by 2 grid. Every single row neatly flips into a column. All right, moving on to Part 2, operations. Now that we know our grids, let's look at how we mathematically combine them. Addition is beautifully intuitive. You literally just add them element by element. The only catch? They must be the exact same order. A 2 by 2 can only be added to another 2 by 2. Scalar multiplication is just as easy. If you multiply a matrix by a standalone number, a scalar, you simply scale every single cell inside that grid by that number. Okay, I'm going to slow down deliberately right here to avoid any cognitive overload, because matrix multiplication is where things get a little tricky. You don't just multiply corresponding cells. Step 1, you can only multiply matrix A and B if the columns of A match the rows of B. Step 2, look at how we isolate just a specific row from the first matrix and a specific column from the second. And step 3, you compute the dot product, meaning you multiply the first numbers together, multiply the second numbers together, and add those results up to fill exactly one cell in your new matrix. So the crucial point here is active learning. I want you to pause this explainer right now, grab some scratch paper, apply that row by column rule we just looked at, and find the product of A and B. Take your time. All right, let's check your work against this isolated breakdown. For that top left cell, we took row 1 of A, which is 2 and 0, and column 1 of B, which is 1 and 2. 2 times 1 plus 0 times 2 gives us 2. If you follow that pattern for every cell, you get 2, 8, 7, and 7. But notice a massive fundamental rule here. If you calculate B times A, you get a completely different matrix. Matrix multiplication is absolutely not commutative. A times B does not equal B times A. Never assume they do. That brings us to Part 3, Determinants and Inverse. Let's step up our architectural builds and extract some really powerful core properties from square matrices. The determinant is a single, incredibly important number that basically tests if a matrix is invertible. For a 2 by 2 matrix, it's super simple. Multiply the main diagonal and subtract the other diagonal, so A times D minus B times C. Now for a 3 by 3 matrix, again we are pacing this slowly so you can see it, you expand across the first row. You take the first element A, cross out its row and column, and multiply it by the determinant of the 2 by 2 chunk that's left. The absolutely crucial thing here, the alternating signs.
Notice it's positive A minus B plus C. That negative B right in the middle is literally where half of all exam points are lost. Don't forget it. Now, these properties here are essentially cheat codes for your exam. The determinant of an identity matrix is always exactly 1. If you swap 2 rows, the sign flips. Most importantly, if you ever spot 2 identical rows in a matrix, you instantly know the determinant is 0 without doing any math whatsoever. Oh, and the determinant of a transposed matrix is exactly the same as the original. Here's the thing. In matrix algebra, you cannot divide. It's just not an operation we do. Instead, we use the inverse, written as a to the negative 1. When you multiply a matrix by its inverse, you get the identity matrix, which remember is our matrix equivalent of the number 1. To find the inverse of a 2 by 2, you take 1 over the determinant, swap the main diagonal elements A and D, and flip the signs of B and C. Notice that part of the formula, 1 divided by the determinant. This is exactly why a matrix only has an inverse if its determinant is not 0. You just can't divide by 0. Time to test your scaffolding again. Pause the explainer here, calculate the determinant of this 2 by 2 matrix first, and then apply that adjoint formula to find the inverse. You've got this. All right, part 4, solving linear systems. Now we get to apply those inverses and determinants to solve complex systems of equations incredibly fast. Imagine a system where 2x plus y equals 5 and x plus y equals 3. As we can see here, there are 2 distinct ways to solve this. On the left is the inverse method, where we use our coefficient matrix to find the answers. And on the right is Cramer's rule, which skips the inverse entirely and uses a ratio of determinants to find exactly the same answer. It perfectly proves our math. Either way, x is perfectly 2 and y is 1. Let's lock in Cramer's rule specifically, as it's a huge time saver for exams. Pause here for a moment. First, find the main determinant d of your coefficients. Then, swap your constant column in for the x coefficients to find dx and for the y coefficients to find dy. Welcome back. Okay, so if you methodically calculated your main determinant d, you should have gotten negative 2. dx gives you negative 4, and dy gives you negative 6. Divide those out, and your final solution smoothly reduced down to x equals 2 and y equals 3. It's just such an elegant, highly structured way to solve equations, right? And that brings us to part 5, eigenvalues and eigenvectors. We've reached the final structural application, a concept heavily used in things like Google's PageRank algorithms, structural engineering, and even quantum mechanics. Normally, when you multiply a vector by a matrix, the matrix rotates and stretches that vector into a completely new direction. But an eigenvector? It's special. Visually imagine a vector arrow being hit by a matrix transformation. For an eigenvector, its direction remains perfectly identical. It doesn't rotate at all. It only stretches or shrinks by a specific scalar value, which we call lambda, or the eigenvalue. To find lambda, you solve the determinant of A minus lambda times the identity matrix equals 0. I know it looks complex, but really, it's just finding the roots of a polynomial. Okay, let's move to our wrap-up and see how this all connects. Here is your ultimate rapid-fire recap table. Seriously, I highly recommend you screenshot this right now. It is your definitive cheat sheet for every single fundamental operation we've covered today, from basic element-by-element addition to the exact formula for a 2 by 2 inverse. Before you head into your exam, beware of these common traps. Remember, never assume A times B equals B times A. Double and triple check those alternating negative signs during a 3 by 3 determinants expansion. Make sure you put the constants in the correct column for Cramer's rule. And finally, here's a massive shortcut. If you have a diagonal matrix, you don't need to do any complex math. Its eigenvalues are literally just the numbers sitting right there on the main diagonal. You now have a complete structural understanding of matrices. So how will you use these invisible numerical grids to code your next big solution?